All right, thank you so much for having me here. It's an honor and a pleasure to be talking about some of our recent work in the field of distributed automation for industrial systems. So industrial automation, what we're talking about is this concept of automation, but now applied to the industrial processes, from robotics to other, for example, manufacturing processes. There's a lot of application areas in industrial automation, this coordination of robots, machines, and everything in a structured environment, including manufacturing, power grids, water treatment, and other critical infrastructure systems. The industrial automation area is rapidly growing. It's going to increase 10% in the next 5 years, and companies are having a more favorable outlook toward incorporating industrial automation in their systems. So the current way that people think about industrial automation is kind of through this ISA 95 pyramid, where things are primarily in this, where information and decisions flow hierarchically based on the time scale that they're made at. However, with recent technological advancements in the areas of all of those buzzwords you hear, cloud manufacturing, industrial Internet of Things, all of those areas, we're seeing some of the flattening in these areas, and we're seeing some of the flattening of this automation pyramid. Now, the robot making decisions about how to drill your part or how to do a material handling process can now have access to information about demand from a customer or some of the logistics information from the enterprise system. This is very interesting, but how do we use that information? And how do we make decisions in this space? Well, to think about this, we can look at some of the challenges for industrial systems today. We don't need to go far. In 2020, the manufacturing systems faced a lot of challenges with the pandemic. For example, in Detroit, we had large manufacturers having to reconfigure their manufacturing systems really rapidly, and industrial control systems did not do a great job, or eventually did a great job, but had to have a lot of engineering time and effort to reconfigure their manufacturing process. We thought this was a one-off, but now in 2025, manufacturing and industrial systems are back at the forefront as we see rapid changes in kind of global and global conflicts and all of the things that are happening these days. So these notions of being adaptable and flexible are coming to manufacturers and industrial systems sooner rather than later. This incorporates several key steps. First, a lot of manufacturers are struggling, or manufacturers and industrial systems are struggling with requests for personalized production. They're struggling, some of them are struggling with integrating new technology, especially as these systems are large and complex. And finally, they have the age-old question of responding to unplanned failures. Note that the last question is not going to get any easier as we integrate new technology, as we account for new requests. So even though that is an age-old question, we now have a new playing field with which to work with. So one of the major challenges is going to be improving the adaptability and flexibility of these manufacturing systems. So one of the ways that we think about this is thinking about this flattened automation pyramid and thinking of these as individual components, intelligent components. This could be a robot on the shop floor, or this could be a logistics program for your enterprise. They have a set of capabilities that they work with, but what we want to mention is that these capabilities now need to incorporate the notions of adaptation and of learning. There's a lot of different definitions out there, but for us, what we were thinking to propose is that adaptation would mean reconfiguring to an existing program. So a mobile robot that can pick up some part, you program 5 different programs, and you pick 1, 2, 3, or 4, or 5. Now learning, maybe you're still a pick-and-place robot, but now you have to have a new part in the system, right? So you have to learn how to pick up a new part. And a lot of the challenges that we see today and a lot of the talks at this conference really focus on kind of keeping those, figuring out how to work with that in those bounds. However, we've seen a lot of robotics applications, and we know that even robots today can do a lot of different things. It doesn't have to be pick and place. They can help with the manufacturing process. So now our goal is to move beyond even those bounds of just their current capabilities, and how do we talk about learning outside those bounds? How do we ask a robot who hasn't seen a manufacturing process to help it do that operation? Now, very broad, very hard, very general question with a lot of potential answers. So I'm going to talk about two of the examples that we've been working on to apply this type of framework, one at the shop floor and the other at the human robot assembly level. So at the shop floor, what I've talked about is there's a lot of components, a lot of various distributed components that are making decisions. We're going to keep it simple, and we're going to say that there's two main components. One will be a product that is supposed to be made, and maybe in this distributed automation setting, that product needs to have a square pocket milled. It communicates with some local environment, and through that communication, it ends up that there's a machine that is able to do that operation. Now we're talking about, again, an automation system. So this is happening all over the shop floor. You have robots that, you have parts that are talking to one another. So how do we organize and coordinate that and ensure that they're flexible and adaptable? That they can adapt to, say, a machine failure, or they can adapt if you want, say, a different color for your car seats, right? So all of these need to happen as we talk about these types of systems. So one of the ways that we've started to think about it is kind of abstracting these systems to these discrete event models where state represents actions of the system. For example, a product may be in one station and it can move to another station, or a machine can do a specific operation. And these event-driven dynamics really model these types of systems well. And you can use these event-driven dynamics to think about automation at that scale. However, what happens when something goes wrong in this system and, say, you're not longer capable? What you want to see is you want to see another robot, another system take its place and replace those capabilities. There's a lot of ways to think about this problem. Two of the ways that were recently published was one that looked at the model-based optimization methods for these types of systems. And recently, we submitted a paper to CASE where we looked at, as everyone has probably played around with, language models to attack some of these problems and create these new states and create these new capabilities that can fill in that void when needed. I'm not going into too much detail, but there's a lot of words in this slide. In general, for this second application of the language models, we provided these controllers with some high-level instructions and task-specific instructions. We were able to encode that model efficiently in a kind of representations, and then we fed it to, say, a language model that asked it to figure out what can we create a new capability for this system, again, at that task level, discrete event system scale, and create that new node and that new edge for that the system can adapt to. It was able to do that, and it was able to reformulate it into kind of the way that we interface with these types of systems effectively, and we were able to see that it worked in this scenario. For that paper, we just did a simple sum of the machines going down, and as you can see from the bottom graph, one of the robots was able to pick up a slack when one of these other machines was sick. So the blue robot was able to be utilized more and went over and helped out to do some material handling operations in this case study. Which was exciting to see. This was done dynamically. This was done adaptively. We didn't tell it can do this operation, but through some of the matching and operations, it was able to figure that out. So these recent technological advances are super exciting, right? They're super exciting because they're enabling us to do this adaptive and learning capabilities that we've thought about the past 5 years, and now we're able to integrate these for these industrial automation systems. The second, we kind of try to take those same ideas to do some collaborative assembly. So everyone has seen this at this point, which is a simple assembly system. But I was talking to a manufacturer, a small manufacturer of about 500 people in the middle of nowhere, Pennsylvania. They're excited about robotics. They want to work with robotics, and they have a robot, but they don't know how to program it and adapt it really well. This is a very common problem, especially in these small and medium manufacturers. So what they want is they want a system that you can interface with and you can work with when doing some of these assembly operations. We were able to leverage some of these language model scenarios. We have a demonstration video that I'm not showing, and we have a paper from last year's case. And we were able to pretty easily integrate language models to and have a person talk with the system. So if a spring is missing, the system can ask, hey, can you bring me that spring component that I need to complete my operation? Now you, as the interface, you can say, no, skip that step. We don't need it for this specific operation. Or here you go, I've placed it, and it's working well. We took this demo actually to automate last week, and we had a lot of different interesting interactions. Some people wanted this robot to do some crazy things, laser print their names, which is kind of difficult to do because it doesn't even have those capabilities. Well, others just said, okay, go, you know? And we saw that our system were able to actually pretty flexibly adapt to a lot of these communication capabilities, even with people who have no knowledge of robotics or have cursory knowledge of robotics. Now, this is not all good and happy things. We see that there's things that these systems are, when commands and when interactions get less specific, that these systems have challenges in adapting to these environments. So as Don mentioned, some of the 9 nines, there's going to be a lot of challenges as we start to play around with these systems and making sure that they're able to work effectively before we can actually apply them in the manufacturing automation systems. So really, the takeaway here is kind of while this integration of new technology is exciting, it is promising. We're able to start thinking about adaptation and learning for these systems in a new way, in this task-adaptive way. The lack of these system-level explainability, safety, and performance guarantees poses extremely challenging problems for adoption in these manufacturing or industrial environments. A lot of these systems are critical infrastructure systems, so this is going to be really vital. In conclusion, we have a new era of manufacturing, a new era, a changing era of manufacturing where things are becoming more flattened, data is available in a lot more places, and we need to develop intelligent components that are able to both adapt and learn from systems. This is an exciting time as a lot of the recent AI and other technologies have allowed us to work in this space more. And this is not only I've given examples in the manufacturing space, but we're also working in integrating power grids and water treatment facilities and leveraging some of this information to make decisions in those spaces as well. With that said, I want to thank a lot of the graduate students who did all of the work, a lot of the collaborators from Michigan, Munich, Penn State, and ETH, as well as my funding agencies. So thank you very much.
Questions for the speaker? Yes, please.
Hi, thank you for your talk. So I saw a page saying explorative learning, and since we are speaking about industrial scenario, the immediate thing I would think about is safety. How do you ever think of how to balance between safety and exploration of your algorithm such that it learn things efficiently while maintaining some sort, you don't want to bump into people.
No, yeah, I mean, you've hit the question on the head. How do we guarantee once we're exploring beyond its capabilities to make safe decisions? That's exactly the question that we're facing right now. Some of the recent work in kind of logic specifications I find promising. So making sure that you're guaranteeing some safety specs, either through temporal logic or other formulations, and then adapting to that you're still meeting those specifications are one of the promising areas that I want to focus on in future work. But yes, it is a very difficult problem. We need those guarantees, and we need those guarantees at the system level.
Thank you.
Hi, this is Satish. I just have a question on the collaborative assembly task. In the shop floor, what would be the best way to have an interaction between the robot and the human? Whether it's an audio communication or is the video or it's a weird form of LED glowing?
Yeah, those are all both great questions. There's two difficult things on the shop floor. One, maybe it's a loud environment, so that's kind of difficult with these spaces. So we do need to account for that. But in a more general sense, a lot of what the manufacturer wanted actually in the next steps of that project is retasking, right? You want to retask it to do a different operation, a bigger part, a caulking operation is what they want to look for next, and they can help the robot. Hey, this isn't exactly what I wanted, or this is you're doing the right thing, keep it going. So those are the things that we want to start thinking about is retasking it. But yes, it's going to be difficult in a manufacturing environment, and this isn't applies to all kind of system.
So how did you made it? It's like in this work. It's like, what is your approach in this work?
Yeah, sure. We have a paper on it, and that goes into more detail. Please reach out to me. I can share that paper with you as well.
Thank you.
Yeah.
Okay, one last quick question.
Hi, this is Sanjay Narayan from Peloton Labs. So your problem you're solving is that you've got lots of robots that do some things. Now you need to reconfigure them to do something else, some other.
Yes.
Okay.
Yeah.
So how do you build a model of the robots as to what they can do so that you can reason about stitch them together to?
No, I mean, yeah, that is a very, very hard question, and I think a lot of people are working at that lower level systems. I think it's difficult. I'm trying to think of it from above a bit of a higher level, the task adaptation level. So yes, modeling those robots, what they can do, from transfer learning or things like that is what we really need to think about. And I honestly haven't thought about it yet. I'm just trying to figure out, can we replace capabilities that we need in the system through these tasks?
Thank you.
Yeah.
Thank you very much for Ilya and for all the great questions.